Hello friends, so today we are going to do the part 4 for the year 2019, and the questions which we are doing today are 9 from mains and 5 are from advanced. So in total we are going to do 14 questions, and this is the last part of this 2019 questions. In the previous part, that is the first, second, third, we only did mains question, and in this part we are going to do 9 from mains as well as 5 from the advanced. So the first question, it states that a parallel plate capacitor is of area 6 centimeter square, a separation of 3 millimeter. The gap is filled with 3 dielectric materials of equal thickness, see figure, with the dielectric constant K1 10, K2 12 and K3 14. The dielectric constant of the material which gave same capacitance when fully inserted in the above capacitor would be. So basic figure is given to us. So we have a parallel plate capacitor, and in this 3 different dielectrics are inserted with the dielectric constant K1, K2 and K3, and we have to find out the equivalent such that within the same capacitor we are going to insert only one dielectric, and based on this dielectric we are going to find out its dielectric constant. And we are given that the area of the plates is 6 centimeter square and the separation is 3 millimeter. Okay. And it says that they are of equal thickness. Okay. So we can say from here that each dielectric is going to occupy 1/3 of the area, okay, because of their equal thickness and aligned vertically, and the distance, or we can say length, of each dielectric will be same, that is 3 millimeter. So here each you can say slab is going to act as a different dielectric. Each dielectric is going to act as a different capacitor. So K1 we assume is acting as a capacitor C1, K2 as C2, K3 as our C3. And we can generalize the equation for each capacitor. So we can say that our each slab acts like a separate capacitor. So we can say C of I will be equal to our K of I epsilon naught A of I and divided by D. Here I is from 1 to 3. Okay, so I varies 1, 2 and 3, and our A of I will be equal to our A by 3. Therefore we can say the total capacitance that is C will be equal to over C1 plus C2 plus C3. So we can expand the given this formula, and we get this over C will be equal to, we can take epsilon naught upon D as common, so we get this as K1 A by 3 plus K2 A by 3 plus K3 and A by 3. And we can also take A by 3 as common. So we can write this will be equal to epsilon naught A by 3D will be equal to K1 plus K2 plus K3. And in the question it is asked that all the, you can say we have to find out the equivalent dielectric, single dielectric. So we are supposed to in this case let us keep this 3 inside, 3 as a common LCM. Okay, and we have to find out the equivalent dielectric, and this dielectric will be a single dielectric. Okay. So the equivalent dielectric single, let us suppose that dielectric constant is dielectric single constant is given as K equivalent. Therefore we can write that our capacitance C will be equal to our K equivalent epsilon naught A and divided by D. So let us this call the equation number 1 and this as equation number 2. So from equation 1 and 2, 1 and 2, we can make 1:1 comparison, and from there we can write that our K equivalent will be equal to K1 plus K2 plus K3 divided by D. And we are already given value of K1 and K2, K3 that is 10 plus 12 plus 14, and we have divided by 3. This comes as 36 by 3 and we get this as 12. So the option C is the correct option. Option C is correct. Next question. It states that an electric dipole is formed by two equal and opposite charges Q with separation D. The charges have same mass m. It is kept in a uniform electric field E. If it is slightly rotated from its equilibrium orientation, then its angular frequency omega is. So we are given a basic dipole, opposite charge Q. So we can just draw an approximate figure for that. So this is our direction of our electric field, and we are having a dipole, and total length of the dipole is D. So this will be D by 2, and we can call this as also D by 2. And we are having, let us suppose this charge here is our plus Q and the lower end is our minus Q. So because of the force, because of electric field on the positive charge, it will be towards the right, and on the negative charge it will be towards our left. Magnitude will be same. And let us suppose we move it by a small angle theta, and mass is given as m. So this is the basic figure for the question. And because of the electric field, there will be two forces, one towards the right, the other to the left, and torque will be, you can say, acting on the dipole due to the electric field. You can say torque on the dipole, we can write this as our tau is equal to P cross E, or we can say this as PE sine of theta. And it is said that we have a small displacement, so we can say that our sine of theta is approximately equal to theta. Therefore, we get our torque is equal to PE theta, and we can substitute value of P, and we get this as our torque will be equal to Q multiplied by D electric field E and theta. And this will be our restoring torque. So you can say that this is restoring torque. Therefore, we can write our torque tau is equal to minus QD E multiplied by theta. And because of the mass that is associated with each charge, we can find out the moment of inertia. We can say moment of inertia I will be equal to, this will be our, there are two mass, so this becomes 2 times m and d by 2 whole square. So this comes as half m d square. Based on this moment of inertia, we can write the equation for the torque. So we can say due to rotational motion, we have our torque tau will be equal to moment of inertia multiplied by angular acceleration, and we get this as I is equal to m d square, and alpha will be our double derivative of the angular displacement, and this torque will be equal to the restoring torque, that is our. So let us call this as equation number 1 and this as equation number 2. So we can say from equation 1 and 2 we get that our minus q d e times theta is equal to half m d square and double derivative of our theta. And we can make some adjustment in this equation. This will be leading us a you can say equation, that is our double derivative of theta plus it comes as twice QE divided by m multiplied by d, and this is our theta is equal to 0. Now this is a standard equation for SHM. can say this is equation for SHM, and we can make a comparison of this equation, that is our double derivative of theta plus omega square theta is equal to 0. This gives us that our omega is equal to square root of 2 QE and divided by m times d. Therefore, we get this as 2 QE m divided by d. So option number A is the correct one. Option A is correct. Next question. It states that the bob of a simple pendulum has a mass 2 gram and a charge of 5 microcoulomb. It is at rest in a uniform horizontal electric field of intensity 2000 volt per meter. At equilibrium, the angle that pendulum makes with the vertical is. So we can just draw an approximate figure for that, and let us suppose this is our fixed point and the initial position of the bob, and this is final position. It moves by angle of theta, and so the forces that will be acting on it, if our electric field is towards the right, so there will be a force because of this electric field, that will be a Q multiplied by E, and in the downward direction we are going to have our mg. There will be tension T, and this tension T can be divided into two components. This will be our T sine of theta, and this will be T cos of theta. So under equilibrium, we can say under equilibrium, our T cos of theta is equal to mg, or we can say T sine of theta will be equal to Q times E, and second equation will be our T cos of theta is equal to mg. And if we divide these two equations, we get our tangent of theta is equal to QE divided by our mg. And we substitute, values are given to us. Charge is about 5 microcoulomb and electric field is given at 2000. Mass is given as 2 gram, so this comes as 2 into 10 to the power minus 3, and G we can take as 10. So we get this as, this entire calculation will be equal to 0.5. Therefore, we can say our theta is equal to tangent inverse of 0.5. 0.5, option D is correct. Option D is correct. Next question. It states that let a total charge 2q be distributed in a sphere of radius r with the charge density given by rho of r is equal to k multiplied by r, where r is the distance from the center. Two charges A and B of minus q each are placed diametrically opposite points at equal distance A from the center. If A and B do not experience any force, then we have to find out a relationship between this A and the radius. So we can draw here the basic figure. So this is a sphere and the radius is our r. Okay, let us suppose this is our center, and 2 points A and B are given that they are placed diametrically opposite and at equal distance from the center. Okay. So this is our center. Let us suppose we have this as A point and this is our B point, and the distance of the two is A from the center O. Radius of this is given as capital R, and here we are given that total charge 2q is distributed on this entire sphere, and the charge density is dependent upon small r, where r is going to vary from center of the circle up till the value of capital R. So in this case we are having, you can say, and this A and B are having the charge of minus q as well as minus q. Okay, so in this sphere total there are 3 charges. One is the total charge on the sphere, and other 2 charges are the charges which are placed at A and placed at B. Okay. So we have to find out if A and B do not experience any force. So first of all, we are going to use this total charge to find out what will be the value of K. Okay. And if Q is our total charge, 2Q is our total charge, that is in the sphere. So we can say our total charge is given as 2Q. So total charge inside the sphere, because the charge density is dependent upon this value of R. So we are going to find out how this 2Q will be distributed according to the density, and that is going to give us the value of K. So total charge is given as 2Q. So we can say total charge inside the sphere. Total charge inside the sphere, and please remember we are calculating it only basis of the 2q, that is the charge which is distributed in the sphere. So we get this as, let us suppose we call this as qt will be equal to integration 0 to r charge density, and we know that this is given as 4 multiplied by volume, and we get this as 4 pi r square multiplied by dr. We substitute value of our charge density, we get our qt is equal to, this comes as 0 to our r, and we have this as kr multiplied by 4r square and dr. And here we can take common as 4 pi k, this comes as 0 to r, we have here r cube and dr, and this total charge, okay, let's integrate first. So this comes as r by 4, and we get this as pi k r 4, and the total charge qt we are calculating it based on this 2q. Therefore we can write our 2q is equal to pi k r raised to power 4. This gives us that the value of k is our 2q and pi r raised to power 4. And okay, so it says that our point, if A and B do not experience any force, so which basically means that electric field at position A or at position B due to charge distribution is exactly cancelled by the electric field due to other charge B. Due to other charge, so it means B cancels A's field and vice versa. So for that we need to find out, you can say, a vector cancellation, and this is only going to happen that if net field at A due to the sphere and B is 0. So we can say that electric field at A, or we can also take and B, due to charge distribution, and here charge distribution we meant by the 2q. Charge distribution is cancelled by the field from other charge, or in simpler terms we can write that net field at A due to sphere and B is 0, or which basically means vector cancellation. Vector cancellation. So we can find out the electric field at a distance A from the center. Okay, that will be electric field due to sphere, because we already found out the value of K, and the charge density is dependent upon the K as well as R. And in this particular case, for point A, our R will be equal to small a. So you can say electric field at distance A from center, and this we are calculating for sphere. So we can say electric field because of the sphere at a distance A. This gives us that K A square divided by 4 epsilon naught. Value of K we already know. This comes as 2Q A square divided by 4 pi epsilon naught, and we have this as R4. And now we are going to find out electric field. Okay, this is electric field at distance A from center at A. Similarly, we are going to find out electric field due to B at A. Electric field at A due to B, and let us write it as our electric field from B to A, and that will be our Q upon 16. This comes as pi epsilon naught A square, and the net electric field should be equal to 0. Okay. And see, net electric field at A is 0. So we can say electric field because of the sphere at a distance A should be equal to electric field because of B at A. And now we can just substitute, and we get this as 2q A square divided by 4 pi epsilon naught R4 is equal to q upon 16 pi epsilon naught A square. And we can cancel the q goes away, pi epsilon naught, and this goes by 2, this goes by our 8, and we are left with A4 and R4. Okay, so this gives us that our A4 is equal to R raised to power 4 divided by 8. And so from here we get that our A will be equal to 1 by 8 raised to power 1 by 4 multiplied by R. So this is the relationship which we are required to find out. And option number A is the correct one. Okay, we can just modify it. It is 8 minus 1 by 4 times A. So our option A is correct. Next question. We are given that charge is distributed within sphere of radius r with the volume charge density rho depending upon r, that is A r square e raised to power minus 2r divided by A, where capital A and small a are constants. If q is the total charge on this charge distribution, the value of radius is. We are given that we are having a volume charge density. Okay, and so based on this volume charge density, so let me write, we are given that volume charge density is given to us as a rho of r is equal to A upon r square e raised to power minus 2r upon A. And based on this, we are going to find out the total charge inside the radius r. We can say total charge inside radius capital R, and we can use a simple formula, that is our Q is equal to integration multiplied by R, and this is a volume charge density multiplied by the dV. dV will be equal to our 4 by 3 pi r cube, so which comes as 4 pi r square multiplied by dr. And we have to remember that this we are solving by using that our charge is equal to integration charge density multiplied by small volume dV, and here V is our 4 by 3 pi r cube. So this is derivative is going to give us this particular formula. We substitute value of this charge density and we get this as 0 to r, and rho of r is A upon r square e raised to power minus 2r upon A multiplied by 4 pi r square, and this is our dr. We can take common as 4 pi capital A is 0 to R, and this comes as our here R square and R square cancels out, so we get this as e raised power minus 2R upon A and derivative of R. And we can just solve the integral, and from here we get this as 4 pi A, and it will be coming as e raised power minus 2R upon A, and this comes as minus A upon 2 and 0 to capital R. Now we can just substitute the values. We get this as 4 pi A by 2, and minus, we can say 1 minus e raised power minus 2R upon A. So this is the value of the total charge, and this is the value of Q. So from here we are interested in finding out the radius, so we can just rearrange it, and we get this as 2Q divided by, so let us cancel this, this comes as 2, and we get this as Q upon, this comes as 2 pi A small a, and will be equal to 1 minus E minus 2R upon A. This will be giving us e raised power minus 2R upon A is equal to 1 minus, and this comes as now Q upon 2 pi A and small a, and this E will be giving us a natural log, so this comes as minus 2R upon A is equal to natural log 1 minus Q upon 2 pi capital A multiplied with small a, and which gives us that our R is equal to, this comes minus A by 2 natural log of 1 minus Q upon 2 pi A and small a, and this is the value of the radius. Okay, we are given here only, there is no negative sign, so we can just convert it to power. So we get our R is equal to A by 2, and this is a natural log of 1 upon 1 minus Q upon 2 pi A and small a. So option number D is the correct option. Option D is correct. Next question. It says that charges minus Q and plus Q located at A and B respectively constitute a electric dipole. Distance AB is 2A, O is the midpoint of the dipole, and OP is perpendicular to AB. A charge Q is placed at P where OP is Y such that Y is very much greater than 2A. The charge Q experiences an electrostatic force F. If Q is now moved along the equatorial line to P prime such that OP prime is Y by 3, the force on the Q will be close to, and this Y by 3 is much larger than 2A. Basic figure is given to us. So we have this A and B having a charge minus Q and plus Q respectively. So this is dipole, and AB is given as 2A. So each side will be our equal to A. Initially our this OP is said to be our Y, and later on we move this charge to P prime, and this is given to us as Y by 3. We have to find out what will be the force at this P prime. So we can just use electric field on the equatorial because of the dipole. You can say that for a dipole, electric field on the equatorial line we can write that our electric field E will be equal to 1 upon 4 pi epsilon naught. This comes as P divided by Y cube, and obviously the direction will be opposite to the dipole moment, and here P is the dipole moment. Let me write this small p, which will be equal to 2AQ. So therefore we can find out the force on the charge Q, and this is with respect to point P. Okay. So let us call this as our EP. So you can say force on charge Q. We get this our force at point P will be equal to charge multiplied by electric field point P, and we substitute we get this our FP will be equal to 1 upon 4 pi epsilon naught, and this comes as 2AQ multiplied by capital Q and divided by Y cube. Now we come to the same calculation we are going to do at Y prime, P prime, sorry. So we can say at P prime we are given that our Y prime is our Y by 3, and we can say that the force at P prime will be equal to 1 upon 4 pi epsilon naught, and this comes as 2AQ, and the distance is our Y prime. Okay. This distance we assume that is our Y prime, which will be equal to Y by 3. So we substitute we get this as our FP prime will be equal to 1 upon 4 pi epsilon naught, and this comes as 2AQ capital Q. Y prime is our, sorry, this is cube, so this comes as Y cube divided by 27, and this entire expression is equal to our FP, and in the question it is given as our F. Therefore we can say our FP prime will be equal to 27 times F. So we get option D is the correct one. Option D is correct. Next question. It states that two identical parallel plate capacitors of capacitance C each have plates of area A separated by a distance D. The space between the two plates of capacitor is filled with three dielectrics of equal thickness and dielectric constant K1, K2 and K3. The first capacitor is filled as shown in figure 1 and second is filled as shown in figure 2. If these two modified capacitors are charged by the same potential V, the ratio of energy stored in the two would be E1 refers to capacitor 1 and E2 refers to capacitor 2. So we have these two different dielectrics, and only the arrangement is different. Okay, so we can respectively draw the equivalent circuit of both these capacitors with respect to their dielectric. So for the first one, this will be K1, K2, and this will be our K3, and they will be connected like this. Similarly, for the second one, we can draw it. This will be K1, K2, and we have this as K3, and they will be connected like this. In the first case, let us say that each dielectric is going to act like a, you can say, different capacitor. So let us call this as C1, C2, and C3. So this is our figure 1 and this is our figure 2. So we can see equivalent capacitance of figure 1. Equivalent capacitance figure 1, and all these are connected in series. So we can write this will be equal to 1 upon, let me call this as CA, will be equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. And the total thickness is our D and area is our A. So here the thickness will be coming as, each thickness will be over D by 3, and of each plate the area will be same. So we simply substitute the values. We get 1 upon CA will be equal to, we get this as 1 upon C1, that is our K1 epsilon naught A divided by D by 3 plus 1 upon K2 epsilon naught A divided by D by 3 plus 1 upon K3 epsilon naught A and D by 3. So we can just solve it now and get 1 upon CA will be equal to, we can take common as D upon epsilon naught A, and inside, or we can say 3 also we can take common. Inside we are left with 1 upon K1 plus 1 upon K2 plus 1 upon K3. And we can take the LCM. So this comes as D 3 epsilon naught A. LCM will be our K1, K2, K3. So this comes as K2, K3 plus K1, K3 plus K1 times K2. So we get our CA will be equal to, we are going to take the reciprocal, so which comes as 3 epsilon naught A divided by D, and coming as K1, K2, K3. This will be K1, K2 plus K1, K3 plus K2, and we have this as K3. Similarly, we can do for our figure B also. Figure 2, and here the thickness of each plate will be, the length of each plate will be d, and the area will be coming as a by 3. And all these are in parallel. Let us say we call this as C1 prime, C2 prime and C3 prime. Therefore, we can write that our CB will be equal to C1 prime plus C2 prime plus C3 prime, which gives us K1 epsilon naught A by 3 D plus K2 epsilon naught A by 3 D plus K3 epsilon naught A 3 divided by D. And this is quite easy to solve now. We get our CB taking common as our epsilon naught A divided by 3D, and we are left with one K1 plus K2 plus K3. So we found out the equivalent capacitance with respect to the respective dielectrics, and we have to find out their, you can say, energy, ratio of energy rather. So energy for first, energy for second will be equal to, they are charged with the same potential, so this comes half Ca V square and half Cb V square. Here half voltage cancels out, so this comes as our Ca upon Cb, and we already know the values. We substitute, this will be coming as 9 K1 K2 K3 and divided by K1 plus K2 plus K3, and we get this as K1 K2 plus K2 K3 plus K1 K3. So this is the ratio of their respective energies, and the option C is the correct option. Option C is correct. Next question. We are given a parallel plate capacitor is made of two square plates of side A separated by a distance d. The lower triangle portion is filled with a dielectric of dielectric constant K as shown in the figure. The capacitance of this capacitor is, basic figure is given to us, distance between the plate is d, area is A, and lower portion is filled by the dielectric which is having a dielectric constant of K, and we have to find out the, you can say, the equivalent capacitance of this entire setup. So first of all, we need to find out our how, let us call this so this is our x-axis and this is our y-axis, and this point is our origin. So at x is equal to 0, y is equal to 0. So you can say at x is equal to 0, y is equal to 0. And when our x is equal to A, our y is equal to D. You can say at x is equal to A, our y is equal to D. So from here we can say the thickness increases linearly. So you can say from here thickness increases linearly, or we can say our thickness y that is dependent upon x is proportional to our x. And with respect to constant proportionality, we can write y of x is equal to our k of x, where this k is our constant of proportionality. And we can easily find out this value of k, and using the boundary condition that at x is equal to a, we can write our y of a is equal to k times a, and y of a at x equal to a is equal to our d. So this gives us that value of k is equal to d upon a. Therefore, we can write the equation that our y of x is equal to d upon a times x. So we found out the relationship between our thickness as well as the you can say the width as well as the length of the dielectric constant. Dielectric, not constant. So let us consider here a small strip like this, and this strip is of a thickness dx, and one second. Yes, and the height of this, let us suppose, is our y of x. Therefore, the height of, because this dielectric will be partially in the, this strip will be partially inside the dielectric, and for that, let us suppose this height is y of x, and other will be in the air, and its height will be d minus y of x. Okay. And or one second, let me do it. This is our y of x, d minus y of x. Okay. And like I said, that consider a small strip dx, and based on this dx, we can say that the dielectric layer of thickness, so this strip behaves as a two capacitors connected in series. Connected in series. Along the separation D, along the plate separation D. So it will be behaving as a two capacitors, and one capacitor will be because of the dielectric layer. So we can say that dielectric layer of thickness, which we considered as y of x, and its equation we already know is d upon a multiplied by x. Okay, and dielectric constant is given as k. And second is our air layer of thickness that is our d minus y of x, and its dielectric constant will be equal to 1. So we are having two capacitors and they are connected in series. And let us suppose that capacitance is equivalent capacitance is our DC, small capacitance DC. So you can say equivalent capacitance of the strip, suppose that is our DC. Therefore we can write that 1 upon DC is equal to we get this as 1 upon we have dielectric constant is k, and this is epsilon naught, and dA divided by y plus, and this comes as 1 upon we have here epsilon naught, and this is about dA divided by d minus y. D minus y. Okay. Here, sake of simplicity, we have just removed this x because it is going to create a confusion. Otherwise, there is no such importance of that. So this we can write y upon k epsilon naught, and our dA will be equal to a multiplied by dx plus d minus y, and this comes as our epsilon naught, and here will be our a times dx. So we can just write that our DC, small capacitance DC, will be equal to, we can take epsilon naught a dx as common, so this will be coming as epsilon naught a dx, and it will be coming as d minus y, so this will be d plus y 1 upon k minus 1. So this is our small capacitance of this small strip, and value of y we already know, so let us substitute it. We get this as epsilon naught a dx, so this will be d plus y is our d divided by a multiplied by x, and we come write this as 1 upon k minus 1, and d we can take common, and we are left with our, or we can keep it as it is, we can just, so we can say total capacitance that our C will be equal to integration 0 to a, and this comes as our DC. So we can write our C will be equal to 0 to a, and we have this as epsilon naught a dx, and we can take d as common, 1 plus x upon a, and this comes as 1 upon k minus 1, and epsilon naught a upon d we can take common, so this comes as epsilon naught a upon d, and we are left with our integration 0 to a dx 1 plus x upon a, and this is 1 upon k minus 1. So this is a quite simple integral, and let me write the result directly, because here 1 upon k minus 1 is constant and this a is also constant. Okay. So we get this will be equal to our C is equal to coming as epsilon naught a square d, and this will be natural log of 1 upon k divided by 1 minus k upon k. And let me check the answer is given in the format. Okay, natural log of k is not in the denominator. Okay, let me rewrite the answer. So this comes as our epsilon naught a square upon d, and this comes as k natural log of 1 upon k divided by 1 minus k. And we are also having k is not in denominator, so we can just write this will be our k, and here we are going to have minus, so we multiply by minus, this will be coming as plus, and we get the answer as option number k minus 1. Option number B is the correct option. Option B is correct. Next question. We are given that there is a uniform spherical symmetric surface charge density at a distance r0 from the origin. The charge distribution is initially at rest and start expanding because of the mutual repulsion. Figure that represent the best the speed of v that is dependent upon this r along with time of the distribution as a function of its instantaneous radius r of t is. So we are given that it is a uniform sphere, dense charge of q, and radius r0. Initially it is rest and it expands because of the repulsion. Okay. So we have to find out, and here we can just use the simple principle of conservation of energy. So we can say total energy at time t at time t, and that will be equal to the sum of kinetic energy, which is about half mv square, and electrostatic potential energy, which is our u of r, and will be given as k q square upon 2r. And total energy at initial radius r0. So we can say total energy at initial radius r0. Initially it is said that it is at rest, so kinetic energy will equal to 0. So we can say our initial energy total will be equal to kinetic energy plus electrostatic potential energy, which kinetic energy is 0 plus this comes as k q square upon 2 r0. This will be equal to k q square upon twice R naught. So this is the total initial energy. Now we can find out the total final energy. Total final energy at radius r of t. So obviously it is having a velocity as well as electrostatic energy. So we can say that our E final will be equal to kinetic energy final plus electrostatic energy final. Kinetic energy final is half mv square and electrostatic energy will be equal to k q square upon 2 r, not r naught. Conservation of energy. Conservation of energy, we can say initial energy is equal to final energy. So we simply substitute it. We get half mv square plus k q square upon 2r is equal to k q square upon 2r naught. And we can simply write this will be equal to, we need to find out a velocity, so we can take, so we can say our velocity v will be equal to, we can take k q square upon 2 will be common, so this will be coming as 1 upon r naught minus 1 upon r. And this will be 2 upon m and its square root. So here 2 and 2 cancels out. So we get this will be equal to our k square q square upon m 1 upon r naught minus 1 upon r and its square root. And we need to find out the graph. So we are going to plot 2 points which will be very easy to find out. First of all, we know that at initial condition our r is equal to r naught and it states that v is 0. And also at our r tend to infinity, our term 1 upon r is going to tend to 0. So from here we can say our velocity will be equal to k q square upon m r naught. And so the initial point of everybody is same, and from our final equation we can say that the slope of v upon r is gradually decreasing. So option number C will be correct one. Okay, because these two are incorrect, because when r is our infinity, velocity is not equal to 0 and it is not, slope is also not changing. So it will be either increasing or decreasing slope, but from the equation there is a gradual decrease. So option C is the correct one. Option C is correct. Next question. It was asked in the 2019 Advanced, and it states that a particle of mass 10⁻³ kg and charge 1 coulomb is initially at rest. At time t is equal to 0, the particle comes under the influence of electric field Et given as E naught sin omega t in I unit vector direction, where E naught is 1 Newton per coulomb. Omega is 10⁻³ radian per second. consider the effect of only electric force on the particle, then the maximum speed in meter per second attained by the particle at subsequent time is. So we have to find out basically the velocity or maximum speed. And this is in under the influence of electric field. So we can write that the force on the particle due to electric field. Force on the particle due to electric field, that is F is equal to Q times E, and E is already given to us, that is our Q times our E naught sine of omega t. And the force we can write mass into acceleration. So we can write this as mass acceleration is dv by dt will be equal to Q E naught, and this is sine omega t. So here we can find out our velocity. So we can say velocity will be equal to, this comes as Q E naught divided by m, and integration 0 to t, and this is sine omega t prime multiplied by dt prime, only t prime in order to differentiate this from t and t prime. That's only purpose of using t prime. So we get this as velocity v will be equal to E naught upon mass m, and this comes as 1 minus cos of omega t, and we want this velocity should be maximum. So we want v should be equal to over v max, and this is only possible if 1 minus cos, or we can say cos of omega t is equal to minus 1. So this entire will be equal to over 2. Therefore we can write v is equal to v max will be equal to 2 Q E naught divided by, sorry, here I missed omega, m omega, and we know all the values. We simply substitute, we get our v max is equal to 2 into 1 into, sorry, 1, and mass is our 10 raised to power minus 3, and our omega is given as 10 raised to power 3. This gives us 2 meter per second. So this is the maximum velocity is 2 meter per second. Next question. It was also asked in the 2019 advance, and it states that a thin spherical insulating shell of radius r carries a uniformly distributed charge such that potential at its surface is V naught. A hole of small area alpha 4 pi r square is made on the shell without affecting the rest of the shell. Which of the statement is correct? So we can just say that we are having initially there is a complete shell, and then there is a shell which is having some kind of hole, and the area of the hole is given. Position of this particular hole is not given to us. Well, we are not interested because we are going to find out, okay, with respect to charge. So we can say that initial configuration means without hole. And without hole, if the total charge is Q, total charge is our capital Q and our radius is our capital R. So based on this, we can say our surface charge density, that is our sigma, is equal to Q upon 4 pi R square. And now we are going to find out the charge on the whole area that is being removed. So you can say charge on whole area, and area of this, you can say the whole is given to us. Let us call this area as our small area, that is our dA is our alpha 4 pi R square. Therefore, charge removed, or we can say charge on the whole area, charge removed, let us call this as dq, and dq will be equal to charge density multiplied by its alpha 4 pi R square. We substitute value of sigma and we get this as dq will be equal to sigma is our q upon 4 pi R square. This comes alpha 4 pi R square. 4 pi R square cancels out. So this comes as alpha multiplied by q. So therefore charge left on the shell after the hole is removed. You can say charge left on the shell will be equal to total charge Q minus charge removed, and we can just write it that charge left, let us suppose our Q prime will be Q, we can take common 1 minus alpha, and before removing we are given the potential as V naught. So we can say potential at surface before removing, which is given as V naught. Therefore we can say that V naught will be equal to 1 upon 4 pi epsilon naught total charge Q upon R. Now we can find out the potential at center after removing dq. Potential at center after removing dq charge, and we can say potential at center V center will be equal to, we are going to simple using the superposition principle with the negative sign. We get this as initial potential V naught minus 1 upon 4 pi epsilon naught, and the charge removed is our alpha multiplied by Q and divided by R, which gives us we can just take V naught common, or we can write, because our V naught, this particular is our nothing but V naught. Therefore we can take V naught and we get this 1 minus alpha, and Next we are going to find out the potential at r by 2. So you can say that potential at point B, potential at point B, and that is our r by 2 towards the hole, towards the hole. Okay, and because this point will be more closer to the hole, so removed charge is going to have more effect, or we can just write it with respect to the equation also. So we can say potential at point B will be equal to V naught, and this comes as minus 1 upon 4 pi epsilon naught. This is alpha q upon r by 2. And here also this particular term is our V naught, sorry, inclusive of this r, this r also. So we can take our V naught as common and multiply. This comes 1 minus 2 alpha. Okay, and we are supposed to find out the ratio center and this. Okay, center was our 1 minus, where it is, yeah, center is about this equation, and we have this equation. So simply we are going to find out the ratio. So we get that our V center upon VB is equal to our V naught 1 minus alpha divided by V naught 1 minus 2 alpha. V naught cancel out, so this comes as 1 minus alpha divided by 1 minus 2 alpha. So option number B is, sorry, C is correct. Option C is correct. And next we are supposed to find out the electric field at the center and near the hole. So we say electric field at center and near the hole. Now originally when there is no hole in the shell or sphere, the electric field inside that shell is 0. But as the hole is made, a small patch is removed, the symmetricity of the particular shell is changed. So we are going to get a net electric field. So we can say that initially the electric field inside the shell is 0. Is 0. But when small hole is made, a small field appears towards the hole. A small field appears toward the hole. So let us consider a point A. You can say at point A, and this is on the axis of a hole at a distance of 2r. On axis of hole, distance 2r. Therefore, we can write the formula that electric field at A will be equal to electric field due to the shell 2r whole square minus and k alpha q divided by missing patch, that is our square. And we already know that our V naught is our q upon, we can say kq upon r. Therefore, the small electric field will be equal to, we can say this will be over minus, and we can just solve it, k theta upon, sorry, k q upon r square will be our common, and this will be our r square 4, and we get this will be equal to our alpha and r. So this get we as, okay, so let me take the common, so we get k q upon, this is our r square, and one upon 4 minus alpha, I think this is left, one second, k, yes, and in the relationship with V naught, we can write that our delta EA will be equal to minus alpha V naught upon R. So it means the field is reduced by the amount minus alpha V naught upon R. I think that was asked. Field is reduced by minus V naught, and it was potential at the center is reduced by one second, electric field at the center is reduced by alpha V naught upon 2R, and we found that there is negative sign minus alpha, yes, it is minus alpha, and so this doesn't contain negative sign, this also doesn't contain negative sign, and the potential reduced is also not over this. So only option C is the correct. Rest are all wrong. So option C is correct. Next question. It was also asked in the 2019 advance, and it states that a charged shell of radius capital R carries a total charge Q. Given phi is the flux of electric field through the closed cylindrical surface of height h, radius r, with its center same as that of shell. Here the center of the cylinder is at a point on the axis of the cylinder which is equidistant from the top and bottom surfaces. Which of the following options is or are correct? Okay. So we are given that we have a cylinder as well as a charged shell. Okay, and radius is r, total charge is q. Okay, in this case we are mostly going to use, or for every part to check or verify, we are going to use the Gauss law. So first of all, let's find out what will be the geometric equation for the sphere as well as cylinder. So we can say for shell, we can write that equation as our x square plus y square plus z square is equal to r square. Okay, it is a shell, so it will be 2D is equal to r square. And it says that the cylinder is being occupied, which is our of radius r, and it is occupied such that it is equidistant from top and bottom surfaces. So you can say for cylinder, you can write the equation will be our x square plus y square is less than equal to r square, and height is given as h. Therefore we can write that with respect to the z-axis it will be minus h by 2 is less than equal to z and less than equal to our h by 2. Let us make it is 3D, much more easier to solve because of the cylindrical equation, z square, and this is our r square. So we can find out the cylinder intersect the shell. You can say cylinder intersects the shell, and that particular equation is both equidistant from positive and negative axis, so that will be a modulus of z is less than equal to square root of our r square minus small r square. So which basically means that the total height of the intersection, you can say from here that total height of intersection is twice, because it is equidistant, r square minus small r square. Okay. And therefore the if we want the given condition that our cylinder as well as sphere must be enclosed with each other, so we can write that to enclose this portion of shell, the cylinder must satisfy the equation, which is our h should be greater than equal to twice square root of r square minus small r square. And from here we can also draw a conclusion that the enclosed charge is proportional to the area of the spherical surface within the cylinder. So from here we can also write that enclosed charge is proportional to the area of spherical surface within the cylinder. Now let us evaluate each of the options. So first option is given that our height is greater than 2r, and our small r is also greater than capital R. So we are given option A. Option A is our height is greater than 2r, small r is also greater than r, and it says that our phi is equal to q upon epsilon naught. So here basically means that the cylinder fully contains the sphere, both radially as well as axially. From here we can say that our cylinder fully contains the shell radially and axially. Radially and axially. Therefore, shell is enclosed. So we can say our charge enclosed will be equal to Q. So from Gauss law we can say our flux will be equal to Q enclosed divided by epsilon naught, which comes as Q upon epsilon naught. So option number A is correct. Now we come to the next option, which states that our H is less than 8 by 5 and R is our 3 by 5 and phi is equal to 0. Okay, then phi is equal to 0, sorry, not and. So we have our option B, which states that our H is less than 8R by 5, small r is our 3R by 5, which gives us that our flux should be equal to 0. And we can find out by the point of intersection by putting small r is equal to 3R by 5. So from here we can say the shell intersects cylinder. We already know the equation, and that will be given as our Z is equal to plus minus, and we have this as capital R square minus, we have this as 3R by 5 and whole square, which will be coming as plus minus 4R by 5. And we are given that our H should be less than 8R by 5. So which basically means that the height of the cylinder is much less as compared to the shell. So you can say from here cylindrical height is too small to reach the shell. Which basically mean that no part of shell is enclosed. No part of shell is enclosed. So which basically means that our charge enclosed is equal to 0. So automatically our flux will be equal to 0. So option B is also correct. Now we come to the option C, which states that H is greater than 2R and R is equal to 3R by 5. So once again, the only difference here is that our condition for H, and we already found out that for R is equal to 3R by 5, the value of Z should be our 4R by 5. So we come to option C, which gives us that H is greater than 2R, small r is about 3R by 5, which gives us that the flux phi should be equal to Q upon 5 epsilon naught. And we just found out that our Z should be equal to plus minus 4R upon 5. R upon 5, and therefore we can say that our height of the and we are given that the height is greater than 2R. So therefore we can say that height of spherical belt enclosed will be equal to, we can write this as 2 times R upon 5, or which basically we can say that the area of the ratio will be equal to 1 by 5. Area of, sorry, not area but area ratio is equal to 1 upon 5. So therefore our charge enclosed, Q enclosed, will be equal to Q divided by 5. Therefore our flux will be equal to Q enclosed divided by epsilon naught, which gives us Q upon 5 epsilon naught. So option C is correct. And we come to the last. Here also the value of R is different, and value of R is our 4R by 5. So we have here option D, which gives us that our H is greater than 2R and our R is equal to 4R by 5, which gives us the flux should be equal to Q upon 5 times epsilon naught. And we can say that height is 2R and radius is 4R by 5. So from one thing is sure, that our shell is fully enclosed. Axially. And radially we can just find out, we can say radially the cylinder encloses the belt of the shell, and where we already know the condition that our x square plus y square square root is our less than equal to 4r by 5. So it means our shell will be cut from the top half as well as the bottom, not half but top from the as well as the bottom. Therefore we can say from here that this cuts off spherical caps at the top and bottom. Top and bottom. So we can easily calculate once again our z, that is equal to plus minus square root of our r square minus small r is given as 4r by 5 whole square, which gives us plus minus 3r by 5. Therefore we can say the height of spherical belt enclosed, height of spherical belt enclosed, and that is equal to over 2 multiplied by 3r by 5. And here we can find out the corresponding area enclosed approximately. We can say area enclosed will be approximately equal to 2q by, sorry, not area but area enclosed, and this will be our area enclosed as per charge. So this gives us 2q by 5. Therefore from here we can say our flux will be equal to q enclosed upon epsilon naught. Q enclosed is our 2q by 5. This comes as 5 epsilon naught, and which is obviously not equal to q upon 5 epsilon naught, which is the option given to us. So therefore option D is incorrect. So only option A, B and C are the correct one. So option A, B and C are correct. Option A, B and C are correct. Okay, so in this question basically we have made a comparison between the radial length as well as the axial length of the our cylinder with respect to the shell. Based on this we found out the charge. Next question. It states that a parallel plate capacitor of capacitance C has spacing D between two plates having area A. The region between the plates is filled with n dielectric layers parallel to its plates, with each delta is equal to D upon n. The dielectric constant of the mth layer is 1 plus m upon n. For very large n, that is greater than 10 to the power 3, the capacitance C is alpha k k epsilon naught a d natural log of 2, the value of alpha is. So here we are going to find out the net capacitance when n layers are inserted inside the plate. This is a basic question. So we are given that the dielectric constant for the mth layer is given as k, and this we have m upon n, and the net effective capacitance of the entire n layer is our alpha. This is our k epsilon naught a divided by d natural log of 2, and we are supposed to find out value of alpha. So basically we are going to find out this c, make a comparison, and we are going to get the answer. And in the question itself it is mentioned that the dielectric layers are in parallel to the plates, so it means all the capacitors are in series. So which basically means if these are the plates of the capacitor, so within this there are layers, and these are the layers, and each layer will be connected in series. Okay. So these are the plates of the capacitor. So within this capacitor each layer will be connected in series. Therefore we can say each dielectric slab forms a capacitor in series. Okay. And the capacitors are from your 1, this is 2, and this goes up till our n. Therefore we can write the equivalent capacitance, that is 1 upon c, will be equal to our summation, and here we have 1 m tends to n, and this comes as 1 upon c m. Thickness of each layer, that is our delta, is given to us, area is also given, and dielectric constant is of k. So we can easily find out of cm. So we can say our cm will be equal to, for mth layer, km epsilon naught a upon delta. We substitute value of delta, that comes as, for mth layer, this is epsilon naught, and delta is given as d upon n. And we can just substitute the given equation for this k of m, which gives us that k 1 plus m by n, and this comes as epsilon naught a divided by d upon n. We can just solve it little bit. We get c of m is equal to k epsilon naught a d, and this comes as 1 plus m upon n. One second. Yes, and anything else is, yeah, okay, we got c of m. So the reciprocal, we can write that our 1 upon c of m is equal to d upon k epsilon naught a, and this comes as 1 upon 1 plus m divided by n. So therefore we can write the total capacitance will be equal to 1 upon C is equal to D upon K epsilon A, and this is summation M1 to N, and this is 1 upon 1 plus M upon N. And if we say let X is equal to M upon N, therefore as N tends to infinity, very high value, we can just integrate it. This will be coming as 0 to 1, and we have 1 plus X dx, and this will be our integration, will be our dx will be our natural log of 1 plus x limit 0 to 1, which gives us a natural log of 2. And so we get 1 upon C is equal to D, and this is K epsilon A, and here we have our 1 upon N natural log of 2. And okay, one second. Here I missed N, so this will be N, and this will be for N, so this also comes as N, and N cancel out. This comes as D upon K epsilon A and natural log of 2, which gives us C is equal to K epsilon A and divided by D natural log of 2, which is our alpha times K epsilon A divided by D natural log of 2. This gives us that value of alpha is equal to 1. Value of alpha is 1. Next question. It was also asked in the 2019 advance, and it states that an electric dipole with dipole moment P0 square root of 2 1 plus I plus j is held fixed at origin O in the presence of a uniform electric field of magnitude E0. If the potential is constant on the circle of radius r centered at origin shown in the figure, then the correct statement is or are. Basic figure is given to us. We are given 2 points A and B, which are lying on the equipotential surface of circle. Radius is r and the dipole is lying at the center O. Okay. So let us this point B and call this as a B prime and this as a A prime. So both the points, this B and B prime, are lying on the equatorial line of our dipole, because dipole is this one, and so equatorial line will be this one. So obviously it is also given that circle is our equipotential, so electric field at B will be equal to 0. So we are given that B and B prime are on equatorial line of dipole, and the circle represents equipotential. Therefore, electric field at B will be equal to 0. So option C is correct. And we can also write it with respect to the equation. We can say that our electric field for a dipole on equatorial line we can write our electric field, that is our dipole, which will be minus P upon 4 pi epsilon naught, and we have a r cube and r unit vector for the direction, and it is directed opposite to the dipole axis. And we just said that at point P or at point B, total electric field is 0. Total electric field is 0. Therefore, we can write the equation that electric field at B will be electric field of dipole plus E naught, and EB is 0. So this equation is 0. From here we get our electric field of dipole is negative of our E naught. And we can use that our electric field of dipole will be our K times our dipole moment divided by r cube. K we know is our 1 upon 4 pi epsilon naught. And if you consider the magnitude only, so we can say our E of dipole, which is equal to our E naught, and this gives us K P naught upon r cube is equal to E naught. So from here we can find out our radius. We get our r cube will be equal to, we substitute value of K, that is 1 upon 4 pi epsilon naught, and this comes as our P naught upon E naught. This gives that our r radius will be equal to P naught upon 4 pi epsilon naught E naught whole raised to power 1 by 3. So this tells us that option number A is correct. And next is about the magnitude of total electric field at any 2 points of the circle is same, and the total electric field. So let us total electric field at A. Okay. Electric field at A, and point A is on axial line of the dipole. Therefore we can write that point A is on axial line of dipole. Therefore our E axial will be equal to 2K dipole moment divided by r cube, and total electric field at A total electric field at A will be equal to EA is our, because of the dipole, plus our E naught, and we just substitute the values. We get electric field at A will be equal to 2 kp r cube plus E naught, and if value of E naught is equal to kp divided by our r cube, so we substitute it, we get our electric field at A will be equal to, this comes as 3 kp upon r cube, but we are given that our dipole moment P is equal to 2p naught p naught by square root of 2. Is given as p naught square root of 2 I plus j, and we substitute it, we get this as our EA will be equal to, this comes as 3k upon r cube, this is p naught square root of 2 I plus j, and it is said that, so this option is incorrect. Next we come to option D, and it said that electric field at any 2 point circle will be same, but which is not possible because of this dipole. Okay, because dipole is going to vary both magnitude and direction depending upon the position around the dipole, or point how does it vary with respect to this, because here we saw that B and A are the points which are lying on the circle, but the electric field at B is 0, whereas electric field at A is non-zero, so this cannot be same. So we can say that dipole field varies both in magnitude and direction. Magnitude and direction depending upon position around, depending upon position of points around the dipole. So option D is incorrect. D is incorrect. So only A and C are correct. Option A and C are correct. I think this was the last question. Yes. So this completes all the questions from the year 2019. So we did this 2019 into 4 parts, and in this 4th part we completed 9 questions from the mains and 5 questions from the advanced. So total 14 questions was covered in this part 4. In part 1, 2 and 3, we only covered the mains question. So this completes from the year 2019. Thank you.